Okay, good afternoon, everyone. We'll start our today's session. So today we are going to do a pocket milling, a three-axis pocket milling, for which I have already written a program. So I'll first give you an overview of the program. Then we'll run this cycle and see how this pocket milling is to be done. So here on the screen, you can see a program. As I already mentioned, that a program is a set of codes. A program is made of different operations that we are going to perform. So I can say a program is a set of codes. We call these we actually set these codes in blocks. So here you can see we have 18 blocks here, starting from 1 and 1 and 1 to n18. So we have got 18 blocks here, and each block here is made of is a combination of different G and M codes, and we can have some special commands as well. So I'll be giving a short overview for this programming, and then we'll start the cycle. So here, block number 1 is actually the program header, in which we provide the dimensions of the workpiece that we are going to machine. So here you can see the work offset, the active work offset is G54, and the blank. So here we have selected the blank as block centered. We can have other shapes of the blank, like we can have cylindrical shape, or we can have pipe, or we can simply have a block. So our workpiece here, as per the program, is taken to be a block centered, because we have set it the center at the center in both the axes, x and y, and for z it is at the top surface. So blank will be here as block centered. Then the width of the block is as 125, the length is as 130, and HA will be the top surface. So it is at 0 coordinate in z axis, and this minus 130 is actually the another end of this workpiece. So here we have some other parameters like traction plane. So once the operation is done, the tool moves to the traction position, I can say. So the traction position here is 100 mm, and the safety clearance is 2 mm. So once one operation is performed, then the tool move in the positive Z direction to do another operation. So that is the safety clearance provided. And the machining stance is downwards. So these other parameters are set in this program header block. Then we have block number 2. So here we have some coding. As you can see, I'll first check whether the screen is visible to you or not. So is the screen visible? Hello, can anyone?
Yes, it is visible, but there is some reflection
Is
in
it
it.
clearly
Yeah.
visible? Okay, fine, fine. So here we have for the rapid movement of the tool. G90 code is used to for the absolute movements of the tool. Then we have a code G53. Uh, G53 is use it to tell the machine that take this movement as per the machine coordinate system. So that's why we use the code G53 for that. Then we are using here D0. D0 is actually the tool compensation cancellation command. So here in this block, we are telling the machine that don't take any length or radius of the tool. Don't consider any length. So this is the cancellation command because we are actually moving z-axis to the starting point. I can say the home position this time, but as per the machine coordinate system. So in block 3, we are using this trap off command. So this command is we have operated any 5-axis program, then this is a cancellation command for that. So for safety, we are just giving this command here. And also, we have one more command as cycle 800. So this is also the cancellation command for 3 plus 2 axis movement of the uh, tool. So here there is a difference in trap off and cycle 800. That in trap off we cancel the 5-axis simultaneous movement, but in cycle 800 we just cancel the 3 plus 2 axis movement. Means that the simultaneous movement of 3 axis XYZ and the simultaneous movement of 2 axis B and C. So this is the cancellation command for that. Then in block 5, we are again using a code G0, G90, G53. So again, we are telling the machine that make B and C axis to their home positions as per the machine coordinate system. So here we are using, that's why we are using here a code of G53. Then in block 6, again, we are using the rapid movement G90, the absolute system. Then we have a code here G54. So we tell the machine to activate this code, this work offset G54, because we have set the work offset, the origin, the reference point within this work offset. So we are actually activating this work offset. Then we are again telling the machine that make C axis to its 0 position. There can be any offset provided to C axis. That's why we are telling the machine to align this C axis as per the active work offset. Then we are providing in block 7, we are giving this code D1. So we this time we are telling the machine to consider the tool compensation, the tool length and the radius while we are going to perform this operation. So here first, I will just simulate the program. Then I will be discussing these cycles. So we are going to machine this contour on the top surface uh, to a total depth of 3 mm. So this will be the moment of the tool, and all other parameters are shown here. Like we are using a tool of 12 mm diameter, and we are using an end mill tool. Then will be performing some more operations. So this is actually we call it as a pocket milling because we are removing material from inside of the contour that we have made. So here we have actually we have this contour, this main contour. This is one of the pockets, and then we have a square shaped pocket here, and we have two more pockets, a circular pocket and a circumferential pocket, or I can call it as a slot. So we are going to machine these pockets on our workpiece that is already installed on the work table, and all the work offsets are set. So now we'll have a look on the program, and we'll see how these shapes are obtained. So here in block 8, we have provided the coordinates to this contour. So in on Siemens control, we have this option that we can, if the coordinates of any contour are known, the contour is possible to be machined here. So simply we have simply provided the coordinates for this contour, and after the contour is drawn, then we tell the machine whether we want to perform pocket milling or we want to perform spigot milling operation. So simply here we have provided all the coordinates. So these are the coordinate values for x and y. Then you can see here we have a this semicircular shape profile here, and we have actually set the coordinates for this shape as well. So here you can see this contour is made by providing the coordinates for all the semicircular shapes here, and then we have combined them as to form one complete shape or contour. So finally, after this complete figure is done, then we tell the machine in block number 9 that we want a pocket milling machining here. So here we have actually provided some of the values like we want a complete machining, the tool we are using, the feed and the RPM of the machine is all set. We have actually calculated this feed and RPM on the basis of the material that we are going to machine. So here our workpiece material is it's a mild steel, and on the hardness of the workpiece, that is the main parameter that we consider while we calculate the feed and the RPM of the tool. So we have calculated these parameters and directly entered here, and also we are providing this feed in mm per minute. So we are using this the metric scale here actually. Then we are telling the machine that we want a rough milling program, rough milling operation is to be performed, and all the other parameters like Z0, the top surface, where it is standing right at the coordinate of 0, then we want to go up to a depth of total minus 3 mm. Then this will be the step over of the tool provided. So once one cycle is completed, then that will be the step over for the tool to go for another cycle, as you can also see here in the figure. So once the tool completes one cycle, it will take a step over of 50% of the total diameter of the tool. Then we have these Z here. This is the maximum in-feed depth. So we are providing a depth of cut equal to 1 mm here for each complete cycle, and we are going to machine to a total depth of minus 3 mm. So there will be 3 passes for this complete uh, contour to be machined. So here also we are providing some finishing allowance. So this allowance is provided so that because we are actually doing a roughing program, so this finishing allowance should be provided here, and we will do a separate finishing operation for this amount of material to be removed from the workpiece. So usually here is the base finishing allowance, while UXZ is the wall finishing allowance. So we are not providing any base finishing allowance because we are not going to perform finishing for the base, because that is a very time consuming process. So starting point, we are setting it automatically. Then the insertion here, how will tool enter into the material, because we are performing a pocket milling operation. So we have set it as helical um, entry of the tool, and we have set other parameters like what will be the maximum pitch of the helix and what will be the radius of the helix. So after setting all these parameters, we accept this. Then we have one more program, one more cycle. Sorry, this is for the finishing of the wall. So here also we have set the required parameters as per our requirement. So the only difference here is we are providing a maximum infeed of 2 mm. So because the material here is that is which is to be removed from the wall is very less, so we can provide some extra depth of cut here. Then this was for the contour, for the first contour. Then we are going for this rectangular pocket also. So similarly here we have set all the parameters here uh, and tell the machine that the coordinates of this shape, the rectangular pocket, like x0, y0, these should be at the origin, because we are going to mill this pocket at the center. And so here z0 will be -3, because we are going to start this pocket from -3 up to a total depth of -5. So the total depth of cut will be -2. So here the width and the length are all set, and the radius for this pocket is also set as 7. Then again, these are the same parameters that we have already set. So then we are going to do a pocket milling program again, but this one will be the circular pocket. So here also we have set all these parameters here: the diameter of the circle, the coordinates of the circle, and all other parameters. So again, for this circumferential slot, we are setting the values like the coordinates and the number of the circumferential slots, the radius of this slot. And here also we have provided the starting angle. So where I want to machine this slot on the workpiece, so it will be set by providing this angle. So the angle here is -65 degrees. That's why we are getting it somewhere here on the workpiece. And also this alpha 1 will be the opening angle of the slot. So this will actually tell us what should be the circumference of the circumferential slot that we are going to machine. Also, we have set here width as 18 mm. Then we are going to a total depth of -2 mm and providing the depth of cut of 1 mm. And also we have given some wall allowance here, which we are going to machine in another cycle. So these three cycles are for wall finishing, the circumferential slot wall finishing. Okay. Then we have this cycle for rectangular pocket wall finishing. And at last, we are also performing the wall finishing of a circular pocket. So after this machining will be over, then we are telling the machine that rapidly move the tool or spindle to this position z-1, but use the coordinate system as machine coordinate system. So here the machine will not consider any work offset, because we are providing a code here G53 telling the machine that we want to move this tool as per the MCS system. And also D0 here is used to cancel the tool length and the radius. So while going to the home position, we are supposed to cancel the tool compensation, the length and the radius. Only then it's possible to send it to the home position. And in block 18, we are again providing a rapid feed, and the absolute system here is used. So absolute system here implies that the measurements are taken from the origin or the reference point. And again we are sending this tool into the home position in y-axis also, and then we are ending this program. So this is the program that we are going to run now. So I just have provided an overview about this program. Now we are going to run this program and see what will be the movements, how will tool move, and that all will be as per the programming that we have written here. So this will be the first contour. I'll just increase some override, some feed here. So whatever the parameters shown here, or whatever the values you can see here, these will be the movements, the actual movements on the machine as well. So we'll be making the shape, we'll be making these four pockets here. You can also see the top view. Now I'm going to execute this program. So here these blocks will be executed one by one. So the complete block is executed at a time. So here we can also see some functions, some G functions that are active functions while I'm going to start this program. So we'll first focus the camera on the workpiece on the front side of the machine. Then I'll start the cycle. So you can see here the workpiece is already clamped, and the offsets are set here. So the offset is at the center of this workpiece, and at a height of at the top of the surface. So now I'll simply start the cycle. I'm just setting some other parameters on the tool list for the flow of coolant. Okay, now we are ready to start the cycle. First, show the movement of the spindle, then focus on the working. I'll stop the external coolant supply. So now I'm providing the feed to the spindle. Okay. So the machining has started now. There is some cutting sound. Maybe you won't be able to hear that. So the movements to this tool are as per the programming, as per the contour that we want to machine here. So this time we are having a depth of cut of 1 mm, and all other parameters like feed and RPM are already set. So actually we can increase the feed because I am only providing the 50% of the actual feed here. So I can control that. Yeah, it's fine. So you can see here the machining of the contour uh, is under process, but the actual shape of the contour is not yet completed. So now I'll just increase some feed here. So here we are using this end mill of dia 12 mm, having the cutting length of 30 mm. So this end mill can cut the material both at the tip and on the periphery as well. So that's why we are using here this I'll just stop the cycle and we'll try to show you the shape of the first contour, and we can just resume the cycle because we have got the options here on Siemens control. So this is the first contour that we have machined. Now this is only a depth of 1 mm here. Now the similar cycle will run again, and so that we'll get a total depth here. So I will be providing the maximum feed now, and I'll just stop the external coolant supply. So you can analyze here how precisely the machine is providing the movements to the tool, and the tolerance here is in microns, or I can say the movements also provided to the tool are in microns. And we are using here the solid carbide tools. So all the tools that we are going to use to machine this workpiece will be the carbide tools. We can have inserted carbide tools, and we have solid carbide tools. Like this anvil is also a solid carbide tool, and also other inserted tools are also carbide tools. And as I already mentioned, the material here is mild steel. So these speeds and the RPM to the tool are calculated on the basis of the hardness of the workpiece, which is mild steel. So what actually is going on here, that we actually call it as 2.5D machining, because this is actually a manual machining. we manually write a program for this by adding some of the default cycles. Here, actually, the movement, the simultaneous movement is in XY, because every time once the one pass is completed, then the machine is providing the depth. Okay, so after the depth is provided, then the spindle is moving in XY direction. So the first pocket is completed. The rough milling of the pocket is completed. Now the wall finishing will be done using this diamond mill of dia, I think 8.5. The material removal here is very less, so we can do this finishing without coolant. But still, it's a better practice to do the finishing by supplying the coolant. You have to- So again, the end mill tool is loaded on the spindle, and pocket number two, a spare pocket, will be machined now. So I will run the cycle now the on full feed, so we can save our time, because after this 3 axis pocket milling, we are going to do 5 axis milling. Now the machining of third pocket is started, the circular pocket. So once the depth of cut is provided, then there is a movement to XY axis. After completing the pass, again the machine is providing a depth of cut, then there is a movement to the XY axis. So we actually call it as a 2.5 axis or 2.5 dimensional milling. Now this is the last pocket. This is actually the circumferential slot. So you can see here how these operations are performed in a very shorter time. So machining time here is very less actually, maintaining the quality, the precision of the shape that we want to machine. So again, the admin will do the wall finishing of these pockets. So this time the movement to the tool is only at the periphery of the shape. So it only moves on the walls of the shape that we have already machined. You can see here, you can analyze how precise, how accurate the movements of the tool are here. Even we are not using the same tool, this is a different tool, but we are exactly getting the accurate movements to the tool. So the cycle is over now. The tool will move to the safe position as as set in the program that we told the machine. We set the program as we wanted to move this tool after the completion of the program to its home position, um, while as per the machine coordinate system. So this will be the safety position. So the cycle is over now. Now we will inspect the pockets, the machining that we wanted to perform, whether it's as per our requirements, as per our dimensions. So we can use this spray gun to remove the chips from the surface of the workpiece. I'll just clean the coolant. So we can actually use the chamfering tool to give some chamfer here on the edge because they are sharp edge. So you can see here now, uh, the required shape has been machined on the surface, and we have actually provided a small depth here so that the cycle time will be low. So you can analyze here the accuracy, the precision of the machine, and how easily we have performed this pocket milling here, because we have actually got some pre-installed cycles on the machine. We just made a contour for the shape and set the cycle on the in the program as pocket cycle. Then, as per the shape of the contour, we got this pocket here. Then again, we have a rectangular square pocket here. So, but if we are going to do it manually, I mean, if I'm going to write a complete coding for this contour, I can say, then the program will be very lengthy and will be very complicated, because while writing it manually, I have to write a code for this movement, this extreme movement first. Then again, I have to write a code for the step over of the tool. Likewise, I have to see how many step overs will be there. So the program will be lengthy. But here on Siemens, on this 5-axis CNC, I have the option that I will just make the contour and tell the machine that I want to make a pocket milling, or I want to do a spigot milling. If I have used a cycle of a spigot milling uh, while added to this contour, then the material have been removed from the outside of this contour. Okay, but here we have done this pocket milling. So we have got four pockets here. This is the contour, and the others are some, I can say, the standard shapes. Like this is a standard square shape. Here we have a radius of 7 mm at the corners, and this circular pocket, it is also a standard shape here. Then we have this circumferential slot. So uh, we exactly got what we have programmed, and the precision, the accuracy is very high here. You will get the scope pinch here. So we are not the feed needs to be set uh, at the low feed will be required there. So now we will be now doing another program because we don't have enough time. So this 5 milling axis program will take much time, because we have so many operations to perform there. So what I'm going to do, I will just remove this pocket, remove the top surface, the top material, so that we can start our new program. So here, before doing that, you can see uh, how complex shapes, how complex can be the shapes that we can machine. So this was all about 3 axis pocket milling. Now I'll directly run the 5 axis program. But before doing that, I'll be removing the material. I'll be doing a facing operation so that we can start our new cycle. So we have finished the pacing operation. Now, as per the program, we have taken this surface as the coordinate for this surface as Z0. So we again have to set the work offset here using Pro. The offset for X and Y is already set. It is at the center, but the top surface needs to be set again. Because I have programmed like that, I have taken this surface as a zero surface, the zero coordinate for z axis. So this is a flat surface. I can touch at any point on this surface. Okay, now this surface will be at Z0. Now we'll be doing 5 axis machining. So we'll first focus the camera on the screen and I will show you the simulation and I will directly run the program. So we have this 5 axis demo final. So this is a program which I have written manually and added some cycles here. So we are actually going to use cycle 800. So we use this cycle for 3 plus 2 axis movement on Siemens control. So this will be a 3 plus 2 axis movement, means that B and C axis can move simultaneously and X, Y, Z axis can move simultaneously separately. Okay. So this is the program. Uh, so we don't have enough time. I won't be discussing this program right now here. So this is all a manual program. So we have got 140 number of blocks here. So I'll just simulate this program and we'll see what's going on. So here, first we are going to remove the material. We are going to do the chamfer milling. So we are going to remove material at one of the edges, as you can see here. So here our workpiece will be rotated, but not the tool. But here in simulation, it is showing that the tool is at some angle, but practically, actually, the workpiece will be at this angle, which is the B is rotated to 45 degrees, and here the C axis is rotated to 180 degree, and we are getting these two chamfers here. Then we'll be performing this circular pocket milling here. And then we'll be doing this thread milling operation here. So I'll just, then we have done two tapping cycles here. Again, on the other side, we'll be doing the same. Pocket milling will be done first, then a thread milling operation to make threads. Then we'll be drilling. Then we will be enlarging the drilled holes, and then we are finally going to perform this tapping operation. So here you can see we have got number of operations. The first operation will be the chamfer milling operation. Then we are going to do a thread milling operation, and uh, then we'll drill two holes, and we will enlarge these holes. Then we are going to perform tapping operation at the end. So you can see here while while we do this thread milling operation, there is a movement for the tool in the XY plane, in the XY direction. But while we when we are doing this tapping operation, so there is only the movement in the Z axis. So this is drilling, this is enlarging, and this is tapping. So I'll simply now execute the program. Now feed override. We have not provided any feed actually. Now we'll focus the camera and I'll provide the feed. Okay, we have started the cycle now. So you can see here we have some movement to the B axis here as per the programming. So we'll first focus the camera, then I'll provide the feed. Just focus this also, this table. You have to show this. Yeah. So you can observe here that first rotation to the B axis is provided. Then there is a movement in the tool because we are going to perform this chamfer milling, and this is the 45 degrees angle here. So we'll be first doing this chamfer milling. So we can actually do machining at any angle here. So this time we have an angle of 45 degree, but we can set it to any angle here. For BXs, we are having a range of minus 35 to 110 degrees. So within this range, we can set any angle and we can perform any operation. So in this way, we can actually perform five axis, or I can say five-sided machining on the workpiece, except the bottom one. And this machining can be done at any angle in the B axis, and also at any angle in C axis. So I'll be using some external coolant and I'll be increasing some feed. So this time we are machining at 45-degree angle provided to B axis. So this is actually the positive angle that we have provided to B axis. So here we are using inserted carbide tool. So we are here going to a total depth of 16 mm. So we are actually taking the increments of 1 mm for each pass. So this time, this is the ninth pass. So we have reached 9 mm, and in total we are going to machine it to a depth of 16 mm. So if we talk about a 3 axis machine, then there you don't find this possibility. You don't machine there at some angle. So this is only possible here on this 5 axis, because this chamfer milling or the machining at some angle can be only done by these two additional axes, B and C axes. So we can't do this chamfer milling on 3 axes, because on 3 axes, if we want to do this chamfer milling, we need to unclamp the workpiece again after we finish it the machining on the top surface. Then we have to clamp it again at this particular angle. We need to set it, and we need to set it manually, I can say. And there are the chance that we will get less low precision But here the machine is actually setting these angles. We have just loaded the component, keeping the face parallel to the work table, the top and the bottom face. But this angle is provided by the machine, and for sure this is the accurate. This will be the accurate. This is the accurate rotation, the accurate angle that we require. So it is because it is provided by the machine. So in TXCs, while clamping the job, we have we require some skilled person to clamp that job. So this will be the last cut. So this part of the program is completed. We have completed this chamfer milling. Now the tool will move to safe position as per the program, and now there will be a simultaneous movement to the B and C axis because we want to chamfer the other side, the other edge of the workpiece. So this is the simultaneous movement of the B and C axis. After the position is set, the tool will approach to its position where it is going to start the machining operation. So we'll be machining one more chamfer here. So actually, I'm providing the smaller plates here so that you will be able to analyze the movements to different axes. So this machining can be done in a very shorter time. Now we have just we this is the last actually pass of this chamfer. So the chamfer milling at these two edges is now completed. Now we'll be doing the other operations. So we'll see the C-axis is moving to back to its normal origin position, and also the B-axis. Now, now the new tool is loaded on the axis, and the B and C axes are positioned at the right angle, which is 45 degrees this time, and we are now going to do a pocket milling using this end mill. So we can actually do any operation at any angle. Like this time, this is our circular pocket milling program. So we can first provide some angles to the axis, and then we can do any T-axis machining at any angle, or I can say at any side of this workpiece. And actually, uh, this is actually 3 plus 2 axis. So actually, this time we are only rotating 3 axes and then 2 axes. So we can have a simultaneous 5 axis movement as well. Uh, that depends on the complexity of the job that is to be machined. So there can be 5 axis simultaneous movement of the axis as well. So that is actually the highest level, I can say, of this machine, that we can have a simultaneous movements to all the axes. So we can make any almost any complex shape on this machine. So this is a manual programming. This is all I can call it as a manual program, because the coding is written manually, but we have got some softwares, some CAM softwares, by which we generate G codes. by which the coding is generated. So we actually use the software, like we have CAM software, we have NX11 software, CAM programming software. So there we actually need a CAD model of the component that we want to machine. So we set up some parameters there, like which shape or what will be the movement of the tool, what will be the depth of cut, what will be the feed. So while using these CAM softwares, we can have flexibility, we can machine complex shapes. So here you can see that we are going to do this thread milling operation now. So we'll be making threads on the internal periphery of this pocket. So I'll just try to show you. So this is the threading tool. So there is a difference actually in thread milling and tapping. So in tapping, whatever the size of the tool is, it just goes in and comes out in Z axis. So there, whatever the diameter of the tool will be, the nominal diameter of that tapping tool. So we can only form the threads of that particular diameter. But here in thread milling, this is a tool of smaller dia, but we can make threads uh, on the holes having diameter greater than this tool. Like if we want to make threads on the hole having a diameter of 50, we can do this with the help of this thread milling tool. So this time the tool is moving in all the three directions, X, Y, and Z. So the thread milling operation is over. Now we'll be doing the drilling operation. So as per the coordinates, so we are machining two holes. Then then we will be enlarging these holes using anvil, because we are going to do the tapping operation, and for that we are going to use M12 tap. So as per the standard, if I am using M12 tap, there if I am going to tap or making or going to make the threads using tap, then the hole diameter is should be 10.25 for M12 tap. So what we are doing here, we first drilled a hole of 8.5 mm dia. Then we have enlarged this hole to 10.25 mm dia. Now we are going to do the tapping operation. So this is the tapping tool and M12 tapping tool. So it will just move. It will just go in and comes out in Z direction. Once the point in X, Y axis is set. So again, the cycle is complete. So we are going to do these operations on the other side of workpiece, but I think I'll stop here now, because we are going to actually repeat uh, these cycles, these operations on the other chamfer. So we will skip that part, and we'll just inspect how our required shape is gained, whether we have achieved what we wanted. So I'll just stop the cycle here. I'll manually move the tool to the safe position. So I'll just clean the chips. Actually, some finishing operation is to be done if we want a better finish, if we want a mirror finish. So you can see here, this is our final shape. So we have machined two chambers at 45, and then we have performed some operations here. So this is a, we'll focus that part. So we have first machined it here at 45-degree angle. Then we have,
Screen is not
uh,
visible, sir.
hello? Yeah,
Screen is not visible.
yeah, say.
So screen is not visible. Blue in
Okay,
color.
just a
Blue,
moment. Yeah,
blue in color.
the screen is not visible. Just a minute. Just a minute. We are fixing it. Is it visible now?
Yeah, sir.
Okay, fine. So we have performed here a pocket milling program. A pocket milling is done here. Then we have performed a thread milling operation here. Okay, so you can see here that we are having the threads on the internal periphery of this hole. Okay, so that we call as thread milling, thread milling operation, I can say. Similarly, here we first have drilled a hole, so a drilling operation is performed here. Then we have enlarged that hole with the help of end mill, and at last we have performed a tapping operation here. So here also you can see that we have head from the internal periphery, and so here the difference is here the tapping tool just goes in and comes out. So whatever the diameter, whatever the nominal diameter of the tap is, our threads will be of that diameter. The nominal diameter for the threads will be that. But for thread milling, we can have a hole of any size, and we can provide threads to the internal as well as to the external periphery of the hole, or whether it's a hole or a spivot. So we can do this thread milling on the internal as well as on the external periphery of the workpiece. So here we can do these operations, or we can form some other shapes. We can do some spivot milling or pocket milling. We can do such programs at any angle of the workpiece, and on any side of the workpiece except the bottom one, and at any point of the workpiece. So here simply we have done to make it simple. We have done these programs, these operations on this chamfer, but we can do any operation like we already have machined this spigot, sorry, this pocket here. We can perform any machining at any part of this surface at any angle with the accuracy and the precision. So for now, so this was about the 3 plus 2 axis. So here, first we provided the movement to B and C axis. This is the C axis and that is the B axis. Then we have provided movement to the XYZ axis. So I'm going to show you some other machined workpieces, some machined jobs that we have already performed. Uh, so I'll be showing you that part also. So here you can see, if you can show both the, yeah. So this component is machined on this 5-axis machine. Actually, we have got this component from Germany, and we were supposed to check the accuracy, the precision of this machine, the alignment, I can say, of this machine by machining this component. So here you can see we have machined spigots on all the 5 sides of this component. So we have got spigot 1, 2, 3, 4, and 5. 5 number of spigots are there on the 5 sides. So we have performed this machining in one single program. Okay, and also here we have machined these corners at some angle. You can see here. So we have machined the corners. We have provided chamfers. I think this is a 45-degree angle, and we have performed other operations like we have drilled here a hole. Then we have enlarged that hole, and we also have performed a finishing operation by boring tool for the boring operation, and this is done for all other spigots as well. So this complete component was machined on this machine to check the precision, to check the accuracy of this machine. So here we have one more component here. So that is also machined on this machine. Uh, so we have got here some spigot milling operations on the top surface. Two spigots are there, and some pocket milling is there. Then we have these same programs, same operations that we have performed on our workpiece right now. Like there is a thread milling operation, pocket milling and thread. This is a square pocket, and there is a drilled hole. And similarly, this is also a thread milling operation. And on the other side, we have also this tapping operation performed here. And in the similar way, we first have drilled here, then enlarged the hole, and performed this tapping here. And this all is done at some angle. So we can machine at any angle, because here we have a minimum movement, or the minimum, I can say, the rotation to the machine is 0.001 degree. So that is the 1,000th part of a degree. And also we have a least movement to the spindle or tool as 0.001 mm, and that is 1 micron. So this machine has got good capabilities to machine complex shapes. And for now, we have just machined only, we have just used a 3 plus 2 axis, or I can call it a cycle 800. So there in these machining programs, we have just provided the simultaneous movement uh, only to 3 axes and then for 2 axes B and C. So this is actually not a simultaneous 5 axis machining. So that simultaneous 5 axis machining is to be done. That is possible only with the help of some software, some CAM softwares. So we, by using CAM softwares, we are modeling the component as per our shape, required shape, and then we generate a G code, G codes from there, and simply install simply. Copy that G code file onto the machine and set the work offsets as per the modeling on the workpiece, and we simply run the program. So 5 axis simultaneous movement is only possible by some CAM software, like we have SolidCAM softwares, we have NX11 CAM software. Uh, this was all the manual programming, and actually we have this option here. We have actually on Siemens control, we have this 3+2 axis rotation, or I can say the option, the cycle available, because that is there is only 3+2 axis movement. Okay, so for now I think we'll be closing our today's section. So so now I was actually actually wanted to do other cycles as well, but at least I can show you a simulation of that part of that program, and then we'll close our today's session here. So yeah, 3 axis milling.
Sir, again, not visible, sir.
Okay, we'll focus it. We'll focus it. Just now, the session is just now for a minute now. So I'll just show the simulation. What I also wanted to machine on that component. I'll just show you the simulation part. Then we'll be stopping our today's session. Now the screen is visible. Is
Yeah,
it?
sir.
Okay. So that was one more program that we wanted to operate. We'll just see the simulation. So we simply wanted to make this shape on the top surface. So this is actually pocket as well as the spike milling operation here. I'll run it once again, and also some drilling operation. So we are also performing some drilling operation here. So that was the complete. So after completing this 3+2 axis, I wanted to run this program as well. So, but I think the time is over now, and we will be closing our today's session now. And I hope this whole session will be useful for you, and I wish to see you people in our coming workshops. And thank you so much. Thank you so much for your time. Take care. And this is all for now.
Sir, today is the last day of workshop.